Okay, so we're taking a look at section 6.2 today. And we're going to be talking about volumes. And I just handed out volumes of paper to you guys. So you should have 3 handouts. One of them has a cone on the front. The other one has, mine's in color, isn't it fancy? Just a bunch of graphs that we're going to be using. It's just going to save us some time so we don't have to do quite as much graph sketching. And they should have an activity also, which we hopefully will get to today. Okay. So basically everything that we've been doing up until this point, we've been talking about areas for the most part. So using integration to find the area under a curve. So just to give you a little reminder of how we were doing that before, I'd have some curve, f of x, and if I wanted to find the area from A to B, okay, so remember that what happens is we get this kind of unique shape that we don't know how to find the area of just using geometric formulas, like area of a triangle or trapezoid or things like that. So, do you remember what we did to approximate the area under the curve? To approximate it before we even got to all the evaluations, before we even got to like antiderivatives and stuff. Yeah, we were using Riemann sums. We were putting rectangles under the curve because it's very easy to find the area of a rectangle. So we were putting a bunch of rectangles under the curve, whether that be the right endpoint, left endpoint, midpoint. In this case, what I'm happening to sketch is the right endpoint approximation, but it really doesn't matter. I just wanted to remind you guys of the general idea of putting rectangles under a curve so that you could approximate the area. So remember, the area ended up being the integral from A to B of f of x dx. This was our definite integral. So remember that, I mean, we talked about this just integral notation in general, but the idea is that when I'm finding the areas of all of these individual rectangles, I'm multiplying the base. The base is some change in the x coordinate, because I'm kind of doing this vertical slicing. This is the base. Okay, and I'm multiplying that by the height. The base times the height gives me the area of one individual rectangle. And then what did we want to do with all those individual rectangles? Add them all up, because that would give us an approximation of the total area. So add them up. Add up the rectangles. I should say add up the areas of the rectangles from A to B. Okay, so that's what that notation was telling us and what it was doing. Okay, so what we're going to be doing now is taking this idea and taking it one more level up and trying to figure out how we can find the volume of something using a similar concept. So with volumes, let's go ahead and just start off with an example. So let's say that we have, consider the region below the function 2x on the interval from 0 to 4. I'm going to add a little bit to this, but let's just start with this region. Okay, so 2x on the interval from 0 to 4. Give yourself some vertical space here. So if I do 2x on 0 to 4, okay, so let's see, at 1 it would be 2, I'll just put in like, I know I'm going to need 8. Okay, so at 1 we'd have 2, at 2 we'd have 4, 3 we'd have 6, 4 we'd have 8. Should be a line. Again, make the points larger if you don't quite make it through. Yes. Okay, so this is the function 2x. So it says consider the region below that function on the interval from 0 to 4. Okay, so that would be this region here. What's the shape of this region? A triangle. So if we wanted to find the area, which is not what we're going to do, but if we wanted to, we could integrate 2x from 0 to 4 to find the area, or we could just use the fact that we know a triangle area is 1/2 base times height. Two options. But what we're actually going to do, we're not going to find the area of this. Let me label my axes here. Let's say that we want to take this region and we want to revolve it around the x-axis. So I want us to think of what that would look like. Revolve the region about the x-axis. Okay, so what I like to do here is think about taking this whole region and we're going to just revolve it around. So you see how a three-dimensional object would get created if I revolved this triangle around an axis? So I'm going to do this to show that I'm revolving the region. And then we're going to think of what that would look like. So actually, I have a prop. I kind of like the red one. I know. You probably saw these when you were picking up those papers. Unrevolve them. Okay. So imagine I have there we go, a triangle, which, ignore this part for right now. That part doesn't really matter that much. But I have some triangle. Okay, if I take that and I revolve it, what gets created? A cone. Here, let me push these little pieces together. There we go. A cone. Okay. So this is actually a Christmas decoration from IKEA. I'm like, oh. It's actually my office mate's. I stole it from her. Borrowed it from her. I have 3 of them up here, so if you want to play around with them at some point, feel free to. But the idea is that we're taking these 2-dimensional regions, and then we're revolving them to create 3-dimensional objects, just like this. Okay. So what that would look like here then is I would take this region and revolve it about the x-axis. The way that I like to draw these is to just think about reflecting the region and then think about revolving the region. So reflecting means just reflect over, right? So it would still just be a 2-dimensional thing if I reflected. So I'd take like -8, it's about down here. Reflect this point over would make it go here, so this distance would be the same as that distance there. And it would just be taking that region and reflecting it over. So that's reflecting, not revolving. I've reflected it. If I revolved it, it'd create a 3-dimensional object. So to show that this is 3-dimensional, we're going to show the revolution part of just connecting these two. It's more of like a circular arc. So we get this kind of sideways lying cone. Just like this one. Sideways lying cone. This one, the bottom part's kind of cool because you guys actually see that very well? Yeah, it's pretty good. Because it had that original little kink right here. It's supposed to look like a Christmas tree. If you didn't figure that out. Yeah. Christmas decoration. Okay. All right, so we're going to figure out, like, how would we find the volume of this cone? Now, do we have geometric formulas for finding the volume of a cone? Yes. Does anyone remember what the volume of a cone is? Yeah. 1/3. I think I heard a pi in there somewhere. So basically it's, the area of the base times the height, and then it's 1/3 of that. So 1/3 pi r squared is the area of the base, and then the height is h. So in this case, I need to figure out what my radius is. So the radius of the base is 8. And what's the height of the cone? 4. And notice this is, because this cone's laying sideways, our height is like a horizontal height, so h is 4. So to figure out the volume, I've got 1/3 pi 8 squared times 4. So let's see, 8 squared would be 64. Need some help on that one. 64 times 4. 256. So 256 pi over 3, which, if you're curious, is about 268.08. Now, I don't have any units here, but if I did, what would be the units of the volume? Cubic units. I'm just going to write units cubed. Okay, and it's units cubed because, well, you know, 3-dimensional objects, volume, have a cubic unit, but you can also see it come up in the math because the unit of the height is units, and then we're squaring the radius, so squared units. Squared units times units give me cubed units. Okay, now, do you see how this was a very, very specific case where we happen to know the geometric formula of this? Okay, we're going to be doing some with things like this, where we have curves, and we're revolving curves around an axis or a line to create three-dimensional objects. Not going to have geometric formulas for that. So we're going to figure out how do we go about finding the volume of just some revolved region that creates a three-dimensional object. Tristan, do you still have a question?
Yeah. So normally we don't put like squares for normal graphs. So why would we put cube for this?
Good question. So normally when we've been talking about areas, we haven't been, every time we find an area, we haven't been saying units squared, right? I think I just wanted to emphasize that we're finding a volume. So whatever our units would be, you wouldn't necessarily have to write this every time, but if you were given units, your result would be the cube of those units for the units. I said units a lot. Okay, so we're going to think about how we'd be able to find the volume of this using integration. The reason why we're using integration is because just like I can find the area under a curve by slicing it up, I can think about finding the volume of this three-dimensional object also by slicing it up. Okay, so I think about taking slices. If I were to just chop this cone like into a bunch of pieces, okay, just chop, 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 to a bunch of pieces. What would each, I'm going to call these cross sections, okay, because I'm cutting it downward into these little cross sections. What would those cross sections look like? I kind of, yeah. Let's see, if I think about, here's a physical thing. If I were to slice this into two pieces, they would be circles, wouldn't they? They would all be circular because to create this object, I did this revolution. I made this circular movement. So these cross sections are going to end up being circular. Let me show you what one of them would look like, for example. Like if I do a cross section at 2, then I'll put dots here. Do that. And then I would cut here and here. And I'm going to put a little bit of width to it. There's one cross section. So it'd be like one slice. There's some width to it, right? But do you guys remember when we did these? What did we want the width of these rectangles to be? Delta x, but to get as close to the actual area as possible, we wanted that to get as small as possible, right? Delta x need to be as small as possible. Same idea here. We want the width of these cross sections to be as small as possible. Now, when we think about the width of the cross sections, you see how because we're slicing this way, just like this one we sliced vertically, the widths were delta x. What are the widths when I slice vertically here? No, they're still delta x because you see how it's some vertical change? See, like some width here, some delta x. Let me draw another one. Here's another way you can visualize these cross sections. Imagine taking a representative rectangle and then revolving that rectangle. You see how that would create this circular disc? So if I revolved that, this would come down here. Okay, but here's my original, yeah, I know. There's my original region that I revolved, and it would create this solid disc. Okay, so, and it still has some width that's a change in x. I'll do one more just for good measure. Okay, so if I sliced it here, okay, some change in x for the width. Ty.
I know for this example you probably wouldn't use horizontal slices.
Yes.
In the example of a horizontal slice, would that be a change in y rather than a change in?
That's an awesome question. So Ty asked, in this case we're doing these vertical slices, and the reason why is because we rotated kind of around this horizontal y equals x, or chopping it perpendicular to the x-axis, making the vertical slices. If we were to slice this way, what would the cross sections look like if we were to slice this cone up with horizontal cross sections? There's still going to be like a circular arc to it, right? It would kind of look like a parabola almost. Like a weird, it'd be really hard to figure out the volume or the area of it for sure. But if you did, like, I'm just going to draw one here, for example. It has kind of a parabolic shape to it, and it would be pretty tricky to do it that way. No, there wouldn't be any holes in the center. Are you talking about for this cross-section or these cross? Yeah, there wouldn't be any holes, because this is a completely solid cone. So if you were to slice it here, it'd be a solid kind of parabolic slice. But they would always have like a flat bottom, wherever you went here. Ricardo?
Wouldn't there always be one like actual cone cross section as you get closer to, let's say, 0?
So the cross sections, think about it this way. When we had, so this was a two-dimensional area, right, overall. But our slices, because our widths were getting smaller and smaller and smaller, we're really kind of taking one-dimensional slices, adding up all those one-dimensional slices to get this two-dimensional area. So here we have these two-dimensional slices that we're going to eventually add all up to create this three-dimensional area. And that's because we're multiplying by the width eventually. Okay. We'll get to that. Let's keep going. Okay, so do you see how wherever I slice, I'm going to have a different size slice? Which x value would create the largest slice? Yeah, like at 4, that would be the largest slice. The smallest slice, well, they get smaller and smaller and smaller. 0 would be the smallest slice. Okay, so depending on where I slice this cone, I'm going to have different areas involved. Okay, so what we're going to do is, in order to find this volume, we're going to think about, if I had infinitely many slices in here, and I found the area of each of those slices, added them all up, I could figure out the volume of this cone. So think about it that way. Or just like we were putting infinitely many rectangles under the curve, we're going to be putting infinitely many cross-sections into the three-dimensional object. So let's think about how that would work. So in order to find volume, we're going to take the areas of all of our cross-sections. Now notice that the area of each cross-section is different depending on where I put it. So it's really the area of the cross-section is some function of x. Wherever I put it, I can figure out what the area would be. For example, like if I put my cross-section at 4, the area would be, well, all of these are circular, aren't they? How do I find the area of a circle? Pi r squared. Okay, so if I put a cross-section at 4, then my area at that point would be pi 4 squared, so 16 pi, times some width, which we're just going to call delta x for right now. Okay, so if I put one, well, let's see, this one here at 2. Okay, so the area of this cross-section would be pi, what's the radius there? I put it here at 2. It's 4. How do we get 4? I mean, it's kind of visually 4, but yeah, it was this line that I reflected, or revolved rather, so all my y values are double whatever the x value is. So here, my radius would end up being 4. So pi, so I had that one wrong, sorry. It wasn't pi 4 squared, it would be pi 8 squared. So this one's pi 4 squared, so 16 pi. And so the area then of the the volume of the cross-section would be 16 pi times whatever delta x is, which we're just going to leave as this arbitrary thing for right now. We'll be doing the integration later. So the idea is that if we can figure out what the areas of the cross-sections are as a function of x, and then multiply by the widths, which are delta x, I'm going to call dx, because we're going to be making those as small as possible. If we can add all of those up from a to b, oh, I'm off the screen, darn. That would end up giving us the volume. So let's see, if we end up doing that. So I need to figure out then, wherever I put my slice, what's the area of that slice? Because this got revolved, my area is going to be pi r squared, anywhere I go. But because all the widths are some delta x, then I'd have to integrate with respect to x. So that's why I wouldn't be able to just say The radius, do you guys all see how the radius happens to be the y value in this case? Radius there, 4, radius here is 2. This one was kind of a random spot, but the radius of my cross-section is whatever the y value is at that point. But I can't just integrate like pi y squared dy because, or sorry, dx. My variables need to match just like they always have. So we want to figure out what is the radius depending on where I put that slice. So find this in terms of x. Okay, well we know the relationship between y and x. Y is 2x. So basically anywhere I go, wherever I put my slice, the radius is going to be twice the x coordinate because of this linear relationship that we have here. So that means anywhere I go, the area is going to be pi times 2x squared. Keep going off the screen, sorry. Okay, let's see what that ends up being. So this is pi times, and then when I square 2x, I need to square the 2 and the x. So this would be 4x squared, which, I'll write it as 4 pi x squared. Now let's see if that works, because this is supposed to represent the areas of the cross-sections depending on where I put that cross-section, depending on where I slice the object. So if I were to slice at 2, for example, well, my area should end up being 2 squared is 4, 16 pi, 16 pi. Okay, so this represents the area of the cross-section wherever I happen to slice. We want to add up all those areas. So I'm going to add up the 4 pi x squared dx. And then the bounds, because this is in terms of x, I need the bounds to be in terms of x. So which x values are used? That is, where would I put the slices? Yeah, anywhere starting at 0 up until 4. So 0 to 4. And now we integrate. 4 pi is a constant, so I'm going to pull that out in front. So yeah, 4 pi, and then the antiderivative of x squared would be 1/3 x cubed from 0 to 4. Now remember, what should we get when we're all done with this? The total volume, which we figured out earlier because we happen to know the volume of a cone, should get 256 pi over 3. Fingers crossed. Okay, so we're going to plug in 4, plug in 0. Let's see, that's 64. And 64 times 4 is 256. So we get the same thing. Which one is easier? It's always nice when you have a geometric formula to use, right? But we won't always have that luxury. And you can actually derive this geometric formula using the idea of integration. Basically, if you were to leave this, instead of this being a 4, if this was h and this was r, then you could derive the 1/3 pi r squared h. That would be a really good exam question. Yeah, you could do the same thing with a sphere, derive the volume of a sphere. Cylinder would be really easy. You just have a horizontal line that gets revolved. Yeah. Okay, let's keep going with this idea. Again, the big picture idea is that when we're trying to find the volume of something that's been revolved, then we can think about, and not even just revolve, but trying to find the volume using integration. We can think about slicing up the object and then figuring out what the area of each slice is with respect to whatever the width is. So in this case, the widths are some delta x. So I want to figure out what the area is with respect to x. Integrate to add them all up. You've got your volume. Okay, let's go ahead and do, I think I'm going to have us do, really quick, we're not going to do this entire handout because we don't have time, but I wanted to at least look at these two things. We're going to do this, the front and the back. So with this one, would it make sense to do vertical slices or horizontal slices if we were going to try to do this approach? Horizontal, absolutely, because if I do a horizontal slice, let's say here at 4, what's the shape of that cross section? It's another nice disc. Okay, and we know how to find the area of a circle, so that's why this is straightforward. What's the width of this cross section? Yeah, change in y, because what we're doing is we're cutting perpendicular to the y-axis, and so we end up getting a width as being some change in the y-coordinate. Okay, and notice that depending on where I put my slice, we get different cross sections. But two things never change. One, the shape of the cross section is always a circle and has an area of pi r squared. Two, the width of the cross section is always some change in y. Those are the two consistent things. What does change is the radius and the area of the cross section depending on where I put those slices. Yeah. A hollow cylinder? You mean like if this was not a cone and it was a hollow cylinder instead?
Cylinder and you drilled out part of the center.
Then when you do the cross sections, we would call those washers, and we'll actually do some where you have some hollow parts. So right now we're just looking at shapes that are completely solid, and when that happens, we call this the disc method. Let me write that down. Because what we're creating, the cross sections are solid discs. Eventually, well, today hopefully, we'll talk about when you have some hollow portions to your object that you do not want to consider as part of your volume because it's hollow. And then you have to, we'll get there, It might be kind of like the area between curves concept. Okay, but back to this. Okay, so this has a width of delta y. Now, I'm just going to flip to the back page here because I just want us to think about cross sections in general for a second. This is a pyramid, and it has a square base of 6 by 6, and it has a height of 9. We also have a formula for finding the volume of a pyramid, but let's say we don't have that and we want to use integration to figure it out. So we'd want to do slicing. Okay, so I want us to think about if we sliced horizontally, if we sliced vertically, what would be the difference and which one would be the easiest approach. So I want you to answer this question. If you cut perpendicular to the y-axis, what are the shape of the cross sections? If you cut perpendicular to the x-axis, what are the shapes of the cross sections? Discuss. All right, so if I slice it this way, what are the shapes of the cross sections? Squares, nice. And hopefully you drew one. I'm just going to pick a y-coordinate here. Looks good. Okay, so it would be kind of like that. Now, of course, just keep in mind that we want to make the width as small as possible. So although what I just drew, technically, the area of the top part of it is smaller than the area of the bottom part of it, but we're going to eventually go and just make it as thin as possible to where they'd be essentially the same. Okay. So we can see then that the area, or so that the cross sections are squares. And what's the width of the cross sections? Delta x or delta y? Delta y, right? So you can see this vertical change here, like that. So the widths are some change in the y-coordinate. Okay, that means then what we'd have to do, if we were going to find the volume of this pyramid, which we're not going to do, we're going to have to do something different with the revolution stuff. But if we were to, we would need to integrate the areas of the cross sections with respect to y, dy. What would the bounds be? That we could definitely do. -3 to 3, 0 to 9. Yeah, so remember, these are where we're putting the cross section in terms of y. So we're slicing from y equals 0 up until y equals 9. Okay? I can have the solutions to this posted, so if you want to play around with it a little bit more and take a look at it, feel free to. Let's go ahead and take out another handout, right? So many handouts today. All right, and we're going to do a few of these examples, and then I'm going to let you guys loose on an activity so you can try these out a little bit on your own. Okay, so with these examples, what we're going to be doing is we're going to be revolving either region A or region B about an axis, like the x-axis or the y-axis, or maybe a line, like a horizontal line or a vertical line. Okay, so let's go ahead and start pretty basic. Let's go ahead and revolve region B about the x-axis. And the idea with all of these is that we're going to want to find the volume of the three-dimensional object that gets created by doing that revolution. If people ask you how your Calc 2 class went today, you should tell them it was revolutionary. Yeah. Okay, so one thing that people struggle with at first is drawing these 3D objects, and I totally get that. I find the easiest approach to take is to begin by reflecting the region and then bring the three-dimensional part in. So if we're going to reflect the region over, this is the x-axis, maybe I'll put my little revolution indicator there. Okay, so you might be able to visualize this in your mind right now, but then putting it down on paper is what we need to do next. So we're going from 0 to 9. So I'm going to put a point here and a point right here. Now, if I revolve the point 0, 0 about the x-axis, what's going to happen to it? It's not going anywhere. It's going to stay there. Okay, but if I revolve this one, where would it go? It'd go down here to -2. So right now it's at 9, 3. It would go down to 9, -3. Now you can do this to as many points as you'd like. The more you do, the more accurate it's going to be. I like to just find my nice points. Square root of 4 is 2, so that's another nice one. That would come down here. Square root of 1 is 1, so that would come down here. Okay, so now I can kind of see where my curve would be if I were to reflect. Again, I'm just reflecting right now, not revolving this graph. Okay? So that's just root x reflected about the x-axis. Now to make it look three-dimensional, anywhere the 2 points are apart from each other, just connect those with a circular arc. So going to connect with a little arc. Little arc. The more you do, the more you'll get the hang of it. Okay, now this shape is it's actually called a paraboloid, if you were curious. OID. Because it's basically a three-dimensional version of a parabola. So we're going to try to find the volume of this. Now we definitely don't have a formula for this, so this is where the slicing is going to become very important. And we're going to think about taking horizontal slices, because what would the shapes be? Nice circles. Okay, so just draw a slice anywhere. It doesn't matter where. I like to call this an arbitrary cross-section. Sounds fancy, huh? Arbitrary because it doesn't really matter where you put it. You're just trying to visualize what a cross-section would look like. So I'll draw one here at 4. And just for good measure, I'll draw another one maybe here at 1. So depending on where I put the cross-section, the area of that cross-section is going to be different. But two things are not different. One, I should say two things are the same. One, no matter where you slice, you'll always have a circle. And two, the widths will always be some change in the x-coordinates, exactly. Which means that we want to integrate our area formula with respect to x, because our widths are some change in x. So looking at this slice, I'm going to kind of think about pulling it out here. I'm going to put it right here, just for visual purposes. Here's one representative slice. Okay, here's the radius. The area of this is still pi r squared. Okay, so Anywhere I go, that's going to be the area, but it's going to be different depending on where I end up slicing. So in terms of x, I want this to be the radius, but I want it to be in terms of the x coordinate. Okay, so if we look over here, do you guys see how, like at 4, for example, the radius is 2? At 1, the radius is 1. At 9, the radius would be 3. Where are we getting those numbers from? It's the square root, right? That's because that's how this curve is defined. The curve is the square root of x. So anywhere I go, the radius is going to be given by the square root of the x coordinate, because that's what the function is. So that's what's going to go here, is my root x. So the area ends up being, well, root x squared is just x, so pi x. So the area of any cross-section, depending on which x coordinate I put it at, is just whatever that x coordinate is times pi. Okay, so notice if I put the cross-section here at 9, my radius is 3, so it would be pi times 3 squared. Well, that would be 9 pi. Well, that's the same as 9 pi. Same thing would work for 4 or 1 or anywhere. So it's always good to spot check your area of the cross-section equation before you proceed. So we have our areas. Now the widths are changing x, so we want to integrate our pi x. Now I like to bring the pi out in front just because it's easier to do it that way. dx, again the dx represents two things. One, I'm integrating with respect to x, but also the widths of all those cross-sections are some change in the x coordinate. What are we thinking for bounds? 0 to 9. Okay, so again, look at what you're integrating with respect to, and then those are the bounds that you're working with. So integrating with respect to x, so I'm using x bounds, and my x ranges from 0 up until 9. Yes? Oh, are you stretching? Just stretch. Okay. Thanks, Ben. All right, so I'm just going to have us integrate using our calculator just for the sake of time. I'm going to just mentally do this one. It would be 1/2 x squared, so it would be 1/2 9 squared minus 1/2 0 squared. So it would be 81 pi over 2. But you can put that in your, well, maybe I should remind you guys how you can put this in your calculator also. Okay, so if you go to F3, this is in a TI-89, and go to integrate. I can show you on an 83 as well. If you have an 83, just stand by. In the 89, you would do, you can either have the pi on the inside, or you can have the pi on the outside of the integral. It doesn't matter which one. So you'd have pi x, comma 0, comma 9. So again, that's integral pi x, that's what you're integrating, comma x, that's like your dx part, comma 0, your lower bound, comma 9, your upper bound. Enter 81 pi over 2. Now if you have a TI-83, you can also, or an 84 or an 86 or any of those ones. What you want to do is go to math, and then scroll down until you get to fn_int, which is function integrate. Enter. Exact same order. Here's the thing with this one though. Leave the pi out for now, because we'll use this to convert to a fraction, and then we'll bring the pi back in. Pi can't be written as a fraction, so we don't want to do the pi part yet. So you do just x, comma x, which seems redundant, but you're integrating x with respect to x from 0 to 9. Enter, and it gives you 40.5. So now we're going to convert that to a fraction by going to math, fraction. So we get 81/2. Now we'll multiply that by pi, so 81 pi over 2. If you were to have the pi in there to begin with, when you hit enter, you'd get 127.234. It is 81 pi over 2, but you cannot convert this to a fraction because it is in terms of pi, and pi cannot be written as a fraction. That's why it's an irrational number. Exactly. So it's square root of 2. Okay, so that's how you can use your calculator to evaluate integrals. Feel free to do that on your homework. If you want the integral practice, it's not a bad idea to maybe just do a handful of them by hand, but if you want to save some time, feel free to do some of the integration on your calculator. Let's go ahead and do one more, and then we're gonna I'm gonna have you guys work on an activity. Let me see. Yeah. Okay. So let's have example 2. This is going to be revolve region A about the line y equals 3. Is that the one I wanted to do? Yeah. So region A about the line y equals 3. So we're not going to go around an axis this time. We're going to go around y equals 3 would be a horizontal line, right? Let's go ahead and start by drawing the line y equals 3. Okay, here's the line y equals 3. And region A. Okay, so let's think about that. So I'm going to again start with reflecting it, and then we'll think about how we can revolve it. So if I do this point right here, if I reflect this point over this line, where's it going to go? Let me go over the line. So notice this is a distance of 3, right? So it's going to go another distance of 3 and go up here to 6. You can do more points if you'd like. This point here is currently 2 units away from the line, so it's going to go 2 units away from the line on the other side. This is, where am I? 4. At 4, it's 1 unit away from the line, so now it's going to be 1 unit away from the line on the other side. Where's this point going to go? Nowhere, right? It's on the line, so when you reflect it, it's going to stay on the line. Okay, so drawing our curve comes to a point. So again, that's just reflecting the curve, and then now we're going to make it look 3D. Notice I'm not doing anything with region B here, right? We're just doing region A over this line. So then fill it in to make it look 3D. Kind of looks like a trumpet. Yeah, kind of. All right, we want to find the volume of this. Before I go into the volume, how are we feeling about the picture? Because once you have the picture, that's when it's much easier. Once you have a visual for it, it's much easier to approach from there. So let's go ahead and draw a few cross sections. There's one. I'm just kind of using the points that I already have. You don't necessarily have to draw this many, but I think it's kind of nice to, just so that, I think I'm just going to do 2. 2 is good. Okay. All right, so we still have the same idea that the area is pi r squared. We just need to figure out what the heck the radius is based on the x or y. What do we think? Are we going to integrate with respect to x or y here? Still x, because we're still taking these vertical slices and our widths are still some change in the x coordinate. Okay, if I did horizontal slices like this, that's when your width would be a delta y, and then you'd have to go from there. Yep.
Why wouldn't we, for the example 1, why wouldn't we use negative root? Because...
Oh, because this is the equation negative root x. You could, but then if you did, you'd have negative root x squared, and you'd still have the x part here. So Ty's question was, why were we using the radius to be root x when also the radius is negative root x? Do you guys see that? Because this equation down here is negative root x because it got reflected. But if you square it, you end up getting the same thing. Here's what I recommend doing, is measuring from the center to wherever your original curve was, not a curve that you sketched. Because you know the exact equation for this is root x without having to think about what the other one would be. And that's going to be especially helpful in this one here. So when I measure the radius, I could either measure the radius from the center up or the center down. What are we thinking? Center down, because we don't know what the equation of this curve is, do we? Could we figure it out? Maybe, but why go there, right? So if we measure from here to here, it's going to be easier for us to figure out what that length ends up being. Tristan?
Is it the same area if you rotate A about the x-axis?
So if you rotate A about the x-axis, would it be the same volume as the one that we have drawn here? No, they'd end up being pretty different. If you revolve A around the x-axis, you'd end up having this hollow portion, which we'll be talking about in a little bit. We'll have a different method for that situation. I think it would end up creating, I'm not sure whether it would be larger or smaller. I'd have to think about that a little bit more. I think we will be doing that one later on, though, so we can compare them then. Yeah. Yeah.
Could you theoretically take the area of the square and then minus,
Yep. Absolutely. Yeah. So yeah, we'll get to that.
Okay.
You guys are jumping ahead. So, all right. So we still have our area, pi r squared. Here's how we find our radii. So, for example, when I slice, when x is 1, what's the radius? And when x is 1? This length here.
Negative 3.
2, right? It goes from here, the radius goes 2 units. Oh, yeah, sorry. When x is 4, oh, you're thinking 0, and my finger was there too. When x is 4, the radius is 1. When x is 0, the radius should be 3. It's kind of hard for me to think of the relationship at the moment, so we're going to need to think about how we can approach this. Well, here's one way we can think about this. If I were to go from this line all the way down to the x-axis, what would that length be? From this line all the way to the x-axis. 3, right? I'll zoom in a little bit. Better. Okay, that would be 3. Now this length, well, sorry, hang on. This, new color. I got new colored pens. Pretty excited about it. So right now this length is 1, right? But do you notice how this length, no matter where I go, will always be 3? But this length will vary depending on where I put my slice. Okay, here it's this high. So really it's whatever the y-coordinate is along the curve is this part right here. So I'm going to call that, well, it's really root x, isn't it? These y values are root x. So I want this distance right here, that distance. The total length is 3. I don't want this piece. What are we thinking? 3 minus root x. Do you guys also notice that's really the top curve minus the bottom curve? Same idea as we've been doing with the area between curves? Yeah? It's the total distance minus the lower one, the top minus the bottom. Okay? So 3 minus root x should end up giving me the radius that I'm looking for. Let's just spot check a few points, because earlier we said when x is 1, our radius should be 2. Notice when we plug 1 in for x, we get 3 minus root 1, which is 2. When x is 4, my radius should be 1. 3 minus root 4, 3 minus 2 is 1. What should my radius be at 9? 0. Ooh, 3 minus root 9? 0. So it checks. So when you come up with an equation, throw some x values in and just make sure it's working the way that you want. Because I see a lot of times people think it should be maybe root x minus 3 instead of 3 minus root x. But think about the top curve minus the bottom curve idea. Okay, so then that means that we want to integrate. Okay, that's the radius, so that means that the area of the cross sections is going to be pi 3 minus root x squared. That's what we want to integrate. And we're not even going to do that. We're going to let our calculator do the work. So pi 3 minus root x squared dx. And the bounds are still 0 to 9, because those are the x values that we're doing our slices. Come here, trusty TI-89. Yeah. Okay, so we're going to put in 3 minus root x squared. Make sure you have appropriate parentheses from 0 to 9. Enter, and I end up getting 27 pi over 2. So this is the volume. Let me put b equals here. 27 pi over 2. Notice that we got a smaller number. Let me zoom out a little bit here. Sorry, you guys can't see anything I just wrote. There we go. Notice that we got a smaller number than example 1. Does that make sense? Based on comparing the volumes. Yeah, this has a much bigger volume, doesn't it, than this one does. I mean, this one gets a lot skinnier towards the end, so that's my best explanation. But just visually, you can see they are definitely two different volumes, and this one has a larger volume than this one does. I think we do need to do one more before I can let you loose on the activity part. So, where did that go? There we go. Because I want us to do one around the y-axis. We haven't done one of those yet. So let's take region A, revolve region A about the y-axis. Okay, so a y-axis one this time. So here's the y-axis, we're revolving around that, and it's region A that we're revolving. So we're going to start again by reflecting and then make it 3D. So I'm going to just pick some of those points, those nice points that we had found earlier. There's really 4 nice ones along the root x function. 0, 0 staying where it is. 1, 1 would go over the y-axis and would go here to negative 1, 1. 4, 2 would go over the y-axis and will go to negative 4, 2. So you're basically going the same distance from the y-axis, just on the other side of the y-axis. This has a distance of 9, so I'm going to go a distance of 9 in the opposite direction, putting it there. Okay, and then filling in the curve part. Okay, and then we'll make it look 3D by connecting these 2 points. It's always a little trickier when they're far away from each other. Kind of looks like those coin machines that you see at the mall, where you drop a coin in and it like spirals around and around and around, and then it goes really fast when it gets to the bottom. Those are pretty fun. I actually saw one of those the other day. You don't see them very much anymore. Okay, so there's our three-dimensional object. We want to find the volume of it. Now, I really only have, I kind of have 2 choices here, but there's one very obvious choice, and that's the way to slice this. Are we thinking horizontal or vertical? Yeah, horizontal, because if I slice it horizontal, I get those nice circular cross sections. We can use the idea of the pi r squared again. So I'm going to just draw a few. I think I'll probably only draw one in this case, just because this one's so narrow, or short, I guess. I can relate to it. Okay, so areas are still pi r squared. The widths, are they a change in x or a change in y? They are a change in y. Okay, so that means that we are going to need to integrate with respect to y instead of with respect to x. Yes. I'm glad we're doing this one right now. Okay, so then basically the idea is I want my area to be pi something squared, and what goes in here should be something in terms of y. Basically, wherever I put my slice, I want it to be in terms of the y coordinate. So if I look back at my cross section here, like I put this one at y equals 2, and I can see that the radius is 4. Okay, if I were to put one here, what would the radius, at 3, what would the radius be? 9. Oh. If I put it at 1, it's 1. Are you seeing a relationship? Yeah, it seems like my radius, wherever I put it, whichever y coordinate I put it at, the radius is the square of that number. So if I put it at y equals 2, my radius was 4. That's 2 squared. When I put my cross section at 3, my radius was 9. That's 3 squared. And that's not a coincidence, right? We have that y equals root x. Do you guys see how the radius of the cross-section is whatever the x-coordinate is at that point? Okay, so I basically want to get this radius in terms of y instead of in terms of x, because my widths are delta y. Well, to solve y equals root x for x, I would square both sides, and I get that if y equals root x, then y squared equals x. So that's what's going to go right here, y squared. So I have the volume as being the integral. I'm going to leave the bounds off for right now, put the pi out in front. Y squared squared, y to the fourth dy. Again, it's a dy because the widths of those cross sections were a delta y. All right, what are we thinking for bounds? 0 to 3. So we basically have two options, 0 to 3 or 0 to 9. 0 to 9 have been the ones that we've been doing so far, and that's because we've been integrating with respect to x, and x ranges from 0 to 9. But we are now integrating with respect to y, and y ranges from 0 to 3. So that's what our bounds are going to be. If you made this a 0 and a 9, what would happen is that you would basically be extending this farther up until you got to y equals 9. So you'd get a much bigger volume, way bigger. Oh, we'll find out how much bigger. Okay, so this is what we're going to integrate. Now, you can type it in your calculator with a y. There's a nice y button on here, so why not? I know, I'm sorry, I'm just so full of it today. You can, of course, make it an x if you want to. It really doesn't matter, okay, as long as these are consistent. So I have pi y to the fourth with respect to y from 0 to 3. And I end up getting 243 pi over 5. Now, let me show you if you did from 0 to 9. Oops, I didn't want an approximation. Well, that's huge, 37,000. Wow, 59,049 pi over 5. Much bigger, way too big. Yeah.
Just for fun.
Yes.
I see every time you're finding the integral for that, you're using a calculator, can I expect that when you put this in the stuff? True.
Maybe not for all of them, so maybe I might have you, some of them I'll say integrate with your calculator. Usually what I'll do is say integrate with your calculator or by hand. Unless I'm trying to get at a fun substitution thing or an integration by parts or something like that. That's why I recommend when you're doing your homework, practice some of them with actual integration by hand, and then other ones you can go ahead and do your calculator if you want to. Yes?
If it wasn't exactly a 0, 0, so we had a hole or something.
Uh-huh.
Over the y or over the x, how
Yeah. So everything we've been doing so far has been completely solid. Every part of the 3D object is solid, and so all of our cross sections are solid. But we can get some parts that end up being hollow. And let me think. I don't know if I think maybe we'll do more of the activity on Thursday. Would you guys be okay with that? If we finished up with lecture, and because I want to teach you guys the washer method too. So let me show you what that would look like. Okay, so example 4, let's go ahead and revolve region A. About the x-axis. Yeah, Ben.
So, will you tell us, the thing that we said, revolve region A about the x-axis, or we have to figure out stuff?
Oh no, that would be in the instructions. So the instructions would say something along the lines of, find the volume of the solid obtained by revolving region A about the x-axis, something like that. Okay, so region A, we want to go about the x-axis. Okay, so let's start by drawing it. So I'm going to kind of pick all the different points of region A. And we can do these ones too. All the nice points basically is what I'm picking. I'm going to reflect all of those, and then we'll fill the rest in. 0, 0 is going to stay. 0, 3 is going to go down to 0, negative 3. That point's going to go there. That one's going to go there. And that one's going to go there. That was pretty. we totally could, and that's how we'll check our answer.
No, what?
Yep. I'll wait till everyone's done sketching and then.
Ooh, different strategy.
Because earlier, we found the volume of revolving region B, right? We found this volume. Now, these are pretty different from each other. I mean, they're similar, but, so, let me explain this one first, and then I'll kind of talk about how we could use something that we already found to help us out with this one. With this one here, it was region A that we revolved, right? So region A is like the solid part of our shape. Region B did not get revolved to create a three-dimensional object. So what happens is that we get this kind of hollow tracing of region B, but this solid part of region A. So if you were to visualize this, if you were to look at this just from the outside, you see how it would just be a cylinder? It'd be like, here's a cylinder, but if you tipped it upside down like this, you would just see this hollow bowl, basically. So it's like a really skinny bowl. You could put Fruit Loops and milk in here if you wanted to. Yeah, it's like a cup, a shot glass. I do not condone that.
There's two different strategies, I think.
Right. So yeah, so one strategy is that we already found the volume of region B being revolved. We found that part already. It was 81 pi over 2. That's the hollow portion of this, right? So potentially, one way I could find this is I could find the, and the outside part's just a cylinder, isn't it? So I wouldn't even have to do any integration. We're going to anyway. But I wouldn't have to find this particular one. I could say, well, I know the volume of a cylinder, let me write this over here, is pi r squared h. And so in this case, it'd be pi, again, I'm thinking about this whole cylinder here. Ignore this part right now, just this outside cylinder. What's the radius? It's just 3, because we're just doing the outer radius. That's just the cylinder. Okay, so just this cylinder here. And then we're ignoring this hollow part for right now, just this cylinder. So the radius is 3, and the height? 9. Now, if I found that, which would be 81 pi, that would represent the entire solid cylinder. Is this shape completely solid? There's a hollow part, right? So we would want to take away the hollow portion, which was 81 pi over 2. So I have 81 pi. I'm going to make it over 2, so that would be 162 pi over 2 minus 81 pi over 2. I guess I didn't need to do it that way. Now it seems obvious to me that that would be 81 pi over 2. Well, it's kind of cool that it ended up being the same thing in the end. It does not always happen, by the way. Think of what made it that way. Might be because it's a paraboloid. So that means that the amount that you could put into this hollow part is equivalent to the amount of solid parts that there is. Which is pretty cool.
Inefficient like that.
Yeah. Yeah, it is very inefficient, isn't it? So let me show you another way we can approach this one using the concept of cross-sections, because we only were able to do this for 2 reasons. One, our outside thing was a cylinder, which was nice, and the inside thing we already had found as being 81 pi over 2. It would not be the most efficient way of approaching this if we hadn't already done some similar examples. So let's say I take this, and I want to do cross-sections. So I'm going to chop, 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 chop. Let's pick one right here at 4, for example. Okay, so what would happen is that this part would be kind of the outside part of our cross-section. Now, if I just stop right there, right now this is a completely solid disc. But would our cross-section be completely solid? There'd be a hollow part to it, wouldn't there? Right here. It'd be this hollow portion running along the inside. So if I were to open this, or like basically take this thing out and rotate it, it'd be circular. but then there'd be this hollow part. Oh, that was terrible. I started so good. There'd be this hollow part inside that circle. So it would look like, if you're familiar with, hardware things. Yes, I just happen to have one of these in my bag. Look like a washer. Be a circle within a circle. Okay, so imagine this washer kind of being along here. It'd be more like, no, the dimensions aren't right. This hollow part looks about right here, but it's not tall enough to be the solid part. Okay, but it would look like a washer. So this is called the washer method, when you have a hollow portion. So if your cross-section is completely solid, you're using discs. When your cross-section has any sort of hollow part, you're using washers. All right, let's figure out how we would approach this. Now, we still want to find the volume, so that is, we want to find the area of this cross-section and still add up all of those areas. Let me draw another one of these just so we can see the visual of this. Okay, so then this is the hollow part. Oh, I have a really cool applet to show you guys too. But let's finish this one up and then I'll show you that. So we're trying to find, so this is the solid part of it. Basically trying to figure out what the area is. Here's the solid component of the cross section. So it's really a circle within a circle. The way that we can find the area of just the shaded region, what do we think? Yeah, pi r squared minus pi r squared, where the two r's are different, right? Here's how we usually approach this, is we call this capital R. Capital R is the big radius, and lowercase r is the little radius. So to find that area, we'd have, maybe I'll write it down here. We'd have pi big R squared, that's the total area, minus pi little r squared, that's the hollow part. So by subtracting those, that's what we're getting. Now to make this a little easier, we can factor out the pi and make this r squared minus r squared. But I want to make sure that we're all clear that what we're not doing is subtracting the radii and then squaring. You see the difference between those two? So I can't just subtract the radius and then square. That would be a completely different area. I need to find the area of the large circle and subtract the area of the small circle. Okay, so don't do that. Nope. I see that a lot. This is why I brought it up. Okay, so let's see. We want the volume then would be the integral. We're still integrating from 0 to 9 because that's where our cross sections are still going. Pi. Well, now I need to figure out what the big radius is and what the little radius is. Do we want this to be in terms of the x-coordinate or the y-coordinate? X, because the widths of these washers is still some change in the x-coordinates. We still want it to be in terms of x. So then what we'd have is, well, let's start with the big radius. I think that might be the easier one. So the big radius gets measured from the x-axis up to here. Does it change? No, no matter where I go, my big radius is always 3. The little radius, the little radius is this distance, which does change depending on where I put my slice. It's whatever the square root of x is, because remember this is basically the y-coordinate of wherever you're at, and the y-coordinate is given by root x. Okay, so it's going to be pi big R squared minus little r squared dx, which would be 9 minus x dx. It's a pretty easy integral, but I'm going to let my calculator do the work anyway. Hey, that's what we paid for it for, right?
Yeah.
Put it to work. Comma x, comma 0, comma 9. Oh, look, 81 pi over 2. Okay, so this is the washer method, and that's the approach that I recommend taking. Like, if my top curve wasn't a nice line, then using the cylinder minus the thing wouldn't have worked all that well. Let me show you a really cool applet before you guys take off for the day.